Everyone thinks they know what reality is, right? You wake up, see the world, touch objects, measure things, and assume that the universe exists independently, objectively, outside of thought. Solid, tangible, and continuous. But wait, here's the thing. What if everything you think is real is more like the output of an incredibly vast, precise computation? What if the universe isn't just obeying rules, it is rules running on something like a cosmic operating system? Think about that for a second. You're sitting in your chair, feeling gravity hold you down, sunlight warming your skin, your computer processing bits and bytes. You're confident that the first three are natural and the last is artificial. But what if the universe itself functions more like the last than the first three? Not metaphorically, literally, that the universe has a computable structure that governs everything from particles to galaxies, from cause and effect to consciousness itself. Let me show you what I mean. Start with something simple. You know how computers work: bits, states, transitions, rules for how one state becomes another. Flip a switch, run a calculation, output a result. Simple, predictable, discrete. Now imagine the universe the same way. Every particle, every field, every interaction is like a computation step. Energy moves, particles collide, photons scatter, quantum states collapse, and all of these events could, in principle, be described as information being processed according to consistent rules. Here's where it gets weird. If the universe is computational, then the apparent randomness of quantum mechanics isn't randomness at all. It's like a complex algorithm generating outcomes that, to us, appear probabilistic but actually obey deep, underlying rules. And that means every law of physics, every constant, every interaction might be the result of a universal computation, a cosmic algorithm ticking away. Now you might be thinking, wait, that's just a metaphor, right? Reality isn't literally a computer. But let's pause and consider the implications before dismissing it. If reality is computable, it explains something profound. Why physical laws are consistent, why constants like the speed of light or Planck's constant never change, and why causality holds across space and time. It's because these aren't arbitrary, they are the rules of the computation, and it's not just abstract theory. Concrete examples appear everywhere. Consider the simple phenomenon of crystal formation. A salt crystal grows according to a discrete, repeatable pattern. The underlying physics can be simulated on a computer. The crystal doesn't decide how to form, it follows a strict algorithm encoded in atomic interactions. Now scale this up. Stars forming from gas clouds, planets coalescing, the evolution of life, all emergent patterns that could, in principle, be described as computations. The universe is computing its own evolution, step by step. But before we go further, we need to look at how humans came to think about reality in this way, because the journey itself helps us understand why the universe as a computer idea isn't just speculative whimsy, it's the logical endpoint of centuries of inquiry. Let's rewind to the 17th century. Isaac Newton is thinking about the heavens. Gravity pulls planets in precise, predictable orbits. Time ticks uniformly. Space is absolute. Newtonian mechanics gave the impression that the universe is like a clock, beautiful, precise, mechanistic. You could, in principle, predict everything if you had enough information. Newton didn't say the universe is a computer, there were no such ideas, but his mechanics planted the seed, that the universe operates according to rules, that the apparent chaos of nature could be reduced to calculable law. The universe seemed deterministic, and humans imagined it as a grand mechanism. Fast forward to the 19th century. James Clerk Maxwell formulated his equations for electricity and magnetism. Suddenly, light is no longer just a particle or a wave. It's a dynamic interaction of fields obeying precise mathematical rules. Maxwell's equations predicted electromagnetic waves traveling at a specific speed, 299,792,458 meters per second, decades before we could even measure them accurately. Here's what's fascinating. The equations work whether you're measuring on Earth or across the galaxy. Why? Because they are computationally precise in the sense that nature follows the same algorithm everywhere. Then comes the early 20th century. Albert Einstein shook everything up with relativity. Time and space are not absolute, they adjust according to motion and gravity. Special relativity shows that the speed of light is the ultimate constant, the limit at which information propagates. General relativity shows that spacetime itself can warp, curve, and interact with matter. And here's the kicker: the mathematics of relativity isn't just descriptive, it's algorithmic. If you know the mass distribution and energy content of the universe, you can, in principle, compute the curvature of spacetime. That's exactly what GPS satellites rely on, solving Einstein's equations in real time to calculate positions accurately. The universe is, at least in principle, solvable like a giant calculation. Meanwhile, at the quantum scale, we encounter a different kind of computation. Max Planck discovered quantized energy levels, leading to quantum mechanics. Werner Heisenberg, Erwin Schrödinger, and others formalize the rules. Wave functions evolve according to deterministic equations. Probabilities emerge when measurements occur. David Deutsch later emphasizes this point. If the universe is governed by quantum mechanics, then it is, at its core, computable. Each quantum interaction is like a gate in a vast quantum computation. Think about Schrödinger's cat for a moment. The cat isn't simultaneously alive and dead in a mystical sense. It's in a superposition, a computational state encoding possibilities. Measurement collapses the state according to precise rules. Random, yes, but constrained, probabilistic, computable. So here's the through line. Newton gives us rules, Maxwell gives us field algorithms, Einstein gives us spacetime computations, and quantum theory gives us probabilistic computations. Each builds on the last. Each suggests that the universe is inherently information processing in nature. Now let's blow minds. If the universe is computable, everything changes, even our notion of what reality means. Consider a thought experiment. Imagine you had a perfect simulator, a computer capable of encoding every particle and interaction in a small region of space. You set it up according to the known laws of physics. Run the simulation, watch it unfold. Would it behave any differently from reality? No. Every law, every interaction, every emergent structure would appear identical. In other words, simulation and reality become indistinguishable if the rules are computable. Now here's the thing, we can extend this. The universe itself could be this simulation, not necessarily simulated by a higher intelligence, but inherently self-computing. Every particle update is a computation. Every photon path, every electron spin, every gravitational wave is a calculation performed according to universal rules. And the constants of nature, the speed of light, Planck's constant, and the gravitational constant, are parameters in the cosmic algorithm. Here's another way to see it. Consider cellular automata like Conway's game of life, simple rules, local interactions, discrete updates. And yet, given enough iterations, incredibly complex patterns emerge, self-replicating structures, gliders, oscillators. Complexity arises naturally from computation. Could the universe's complexity, from galaxies to life itself, emerge similarly? Many physicists, including Stephen Wolfram and David Deutsch, argue yes. Computation isn't just a metaphor, it's explanatory. And now think about entanglement. Two particles separated by light years, yet correlated. At first glance, it seems spooky, like information is traveling faster than light. But if the universe is fundamentally computational, entanglement is just a state update in the universal computation, not a violation of causality. The spooky action is built into the algorithm. It's like two cells in a spreadsheet updating according to the same formula. They remain correlated because the formula ensures it. Concrete example: quantum teleportation. We can transmit the quantum state of a particle without moving the particle itself. Information is being reconstituted elsewhere, following precise computational rules. This is the universe calculating states, not matter physically traveling instantaneously. The computation is primary, the particle is the representation. Now here's what you'd expect, but that's not what happens. Classical intuition says, if reality is a computation, it should be discrete, step by step, like a classical Turing machine. But quantum mechanics shows reality can exploit superpositions, parallel computations, and interference patterns. Nature doesn't just compute serially, it computes in parallel universes of possibility, collapsing outcomes in accordance with probabilistic rules. Reality is both discrete and probabilistic, deterministic and uncertain, classical and quantum. Let's make it even more tangible. Think about your smartphone. Every app, every pixel, every touch is a computation, and yet you accept it as real in your experience. Now imagine the universe itself as a giant quantum computer, constantly updating every particle, every field, every moment. You are simultaneously the programmer, the observer, and the computation. That's not just philosophy, it's a literal description if reality is computable. What does this mean for us, for life, for knowledge? First, it changes how we approach physical laws. No longer are constants arbitrary, they are parameters of the algorithm. If we understand the computation, we can predict and perhaps even manipulate reality more effectively. That's the promise behind quantum computing, synthetic biology, and advanced simulations. They are attempts to tap into the universe's computational rules. Second, it reframes consciousness. If reality is computational, then cognition, decision-making, and even free will could be emergent phenomena from complex information processing systems. This doesn't reduce experience to nothing. It provides a mechanistic framework to understand it. Human minds become sophisticated sub-algorithms embedded within the universal computation. Third, it informs cosmology. Why does the universe appear fine-tuned for complexity? Why do stars, planets, and life emerge naturally? A computational perspective suggests that universes with consistent, computable rules naturally produce complexity. Our universe is not random, it's algorithmically structured to support the emergence of structure, information, and observers. Now here's the everyday connection. GPS satellites rely on Einstein's computations of spacetime. Quantum cryptography relies on computations of entangled states. Even the weather forecast relies on enormous computational models. You live inside a computation, interacting with computations all around you. Understanding that computation at the deepest level illuminates why the universe behaves predictably yet marvelously. Finally, consider discovery itself. Science is essentially reverse engineering the universal computation. Every experiment, every simulation, every theory is an attempt to read the code, to anticipate the algorithm. Discover Newton's laws and you see the rules of motion. Discover Maxwell's equations and you glimpse the logic of fields. Discover relativity and you understand the computation of spacetime itself. Discover quantum mechanics and you encounter the algorithm behind probabilistic outcomes, and each discovery triggers the next, an avalanche of understanding. The more we uncover, the more questions we can answer. The more we reverse engineer the computation, the more of reality becomes accessible, manipulable, and comprehensible. So when you hear someone say, "The universe is a computer," don't dismiss it as a metaphor. It's an invitation to rethink what exists, what is possible, and what it means to observe, compute, and be. Every photon, every quark, every neuron might be a calculation, and you are both participant and witness in that cosmic computation. Reality isn't just happening to you, it's computing itself constantly in ways that obey rules far deeper than intuition or observation. And the journey of discovery, of reverse engineering those rules, unfolds like an avalanche, building momentum with every insight, every experiment, every thought. One discovery triggers another, cascading into new layers of understanding, until what once seemed impossible becomes inevitable, and what once seemed mystical becomes graspable. So the universe as a computer isn't science fiction. It's a lens to understand causality, complexity, and consciousness. It's a framework connecting Newton to Deutsch, Maxwell to Schrödinger, Einstein to every quantum engineer, every theorist, every curious mind. And most importantly, it changes how we see ourselves, not as passive observers in a chaotic cosmos, but as participants embedded within a magnificent, computable structure, playing our roles in the algorithm of existence.